So first of all, there's a little bit of introduction. So, what do we use reordering? Reordering can be used as a step in machine translation pipeline, and it is normally used before the translation step itself. In case you use phrase-based model, it doesn't account for long-range reordering, so we help phrase-based models with reordering step. So, short overview of what you can expect in this presentation. So, first of all, I will describe tree-to-string model for those who aren't familiar with it. Then I will describe how we actually implemented it, and then I will show you the results. Well, actually, you've already seen them. Here, I will mostly focus on the model itself, because, well, our paper mostly looks like instruction how to use models. So, let's move on. So, tree-to-string models actually processes parse tree and forms a reordering sentence, which isn't a tree, just a plain sentence. Normally, people don't speak well, like reorder sentences. Maybe in some fictional characters will do that. So, how can tree-to-string model actually help us? So that's our original sentences, let's say. Hey. We want to make something like series binding requires skill, much does not. So what we do first, we swap two nodes here, which correspond to much and skill. I get three like this. Then we do another two swaps. They can just be, seem to be like one reordering BP node, the higher one into the first position. So another view of a tree is a set of spans, and that's what Moses uses inside, so I think it's very important. So we can say that each node covers some span inside a sentence. Here there are single word level spans which are normally parts of speech, and there are higher level spans which correspond to syntaxis structures. So after the reordering, some spans actually make sense and some do not. Here we're lucky enough to say that every span actually is consistent. So let's talk a bit about consistency. Consistent spans are those spans which don't break after reordering. So there is no word that gets inside the span. So as an example here, well, here all spans are consistent, but if we could imagine that there would be an extra word which would come between skill and much, the span would become inconsistent. There is another way to define consistency. Usually that way is shown for hierarchical phrase-based models because there it is more important. So here we can say that each span covers several words, and those words, if we draw a table and select the cells corresponding to the alignment, then those black cells in a set of rows may fit into a rectangle, and sometimes that rectangle is a square. So if it is a square, then the span is consistent. Now we'll talk about the extraction of rules for tree-based reordering system. So it's actually the same idea as in our tree-based machine translation. So we take one span, we take its subspans, and we try to we calculate the number of occurrences of certain reordering of such span. So here we have all spans are consistent, so we don't need to rely on anything. If we ever meet an inconsistent span, actually we will. If we do need an inconsistent span, we simply remove it from the tree and attach all the nodes nodes below to the high nodes. So here we can see different ways to represent a higher level VP span. So easiest way is simply to take the highest level nodes and just below the VP. So that would be 3 nodes on the high picture. And that would give us room of reordering VP into the front position for those 3 spans. Another way is actually to use some lower level spans, like in the second example. We can actually even use the birds themselves, and well, there is an example of 4 spans, which still form the higher level one. Technically, you could also generate rules which are which don't depend on the syntax labels. That would be more common to hierarchical translation without use of syntax spans, and that would be marked as X. Then let's talk a little bit about decoding. So general idea about decoding is that for every possible span you find, you generate some limited number of hypotheses, and you start from single word spans, just because they are never reordered, and then you increase the number of words. It's a dynamical programming approach. So I will demonstrate it in this diagram. That's called a chart normally. So how it works, every node in the chart has stacks of, well, stack is just a list of hypotheses. So supposing you have generated hypotheses for several layers from below, so let's say for last 4 layers on this picture, you may generate hypotheses for higher ones. So here you see 2 ways of generating hypotheses. One would be to take those 3 words, those 4 spans. 3 of them are actually just single words. Another way would be to use higher level span instead of 2 other spans. Now you may already have a question why we need all those X nodes here, and the reason for that is that sometimes you can't generate the reordering of a sentence just using the rules you have extracted. Just if you haven't encountered something, then you will need something else. That's normally called the glue rule. So what it does, it glues 2 spans together without reordering. So that's kind of an example. You can generate some hypothesis for the left X node. You would probably do it in the same way, so because you can't apply another rule to X node. And then you would have some hypotheses in another node, and they together form another hypothesis. They could actually even go into the marked nodes. So it could be used later with some normal rules as well. So now let's talk about our limitation. It's very simple because well, it's just using modus with some number of trees. So first of all, those who don't know one familiar with modus, it's a very popular open source toolkit for machine translation. It has a decoder and it has a tool to learn the models. So it does everything like in one script easily, so we use it for mainly anything. It has 2 decoders. One of them is phrase-based, which is used if you want phrase-based model. There is chart decoder, which is used for hierarchical and tree-based models. So the training part was done with all those magical screens Moses has. The main parts of them are called an extract tool and score tool. What they do is, well, extract tool does exactly what I described earlier. It extracts all possible rules, and score tool counts their frequencies and assigns them several scores. We also used our training corpus as corpus for language model. Well, that's not very typical. It's rather sparse, and our language model is actually phrase-based and grammar model. Now, as decoder, we use chart decoder, which is built into Moses. Then there was two actually important tricks we needed to implement here. First of all, in this particular shared task, we knew which words should not appear in the sentence, so we say that's dropped words. We could actually use this information. What we did, we replaced all these words in the original sentence with a special symbol, and then we made a rule which would drop that symbol. We use that for training as well, so in training corpus we also did that substitution. And another trick which required some changes in Moses code base was to reconstruct the alignment itself, because it can be ambiguous in case two words occur in the same sentence, two exact similar words occur in the sentence. Usually those are either prepositions or articles or any other controlling class of speech. So what we did, we had to store the alignments in the phrase table. It's actually a rule table, and we had to use that information during the hypothesis construction. So now that feature is available in Moses. Before this workshop, it wasn't. So last part of training is tuning. We tried two different tuning engines. Both are available in Moses. One MERT and another one is Mira. It appeared that Mira was slightly better than MERT. However, it was took slightly longer to converge. So I will then show you the results for both submodels. Now, just so that you can imagine how many weights we were tuning, we had 7 weights in total. One was for language model, and in terms of more than 6 were for translation model. There were 1 weight in translation model that actually corresponded to the rule. 5 other weights were some different conditional probabilities and word count weight as well. Now let's talk about the results we have. So we implemented it, well, the implementation didn't depend on language at all, and we had a chance to test it on 3 different languages. So, as a baseline, I think we were using a system which didn't change the word at all. Now, our main focus was English to Farsi at first, and we only tested it on other language pairs later. So, for English to Farsi, we have detailed results for different options we had in our model. So, first one is when you, well, what I call naive word dropping is when you drop words after you have constructed the translation. And, well, the rule for word dropping is exactly substitution of words which are to be dropped with a special symbol. Now, as you see, the special rule actually gave significant gain in all metrics used, and mirror versus Mac isn't as significant, but still it is quite stable. So those are results for development set in which to proceed. Now let's see the joint table for evaluation set. You have already seen that table probably. You may see that in the book, in the shared task report as well. So we gained blue over baseline in every language pair. And so, well, still there are some ways to improve because due to time constraints, we couldn't implement all the ideas we had. So those would be ideas that I would suggest if anyone would like to do this themselves. So, first of all, the problem is that parser sometimes does have some errors, and our approach is very sensitive to those errors sometimes. So, especially it falls if you have many immediate children from one node, then you simply can miss good Reordering hypothesis if there is one correct parse error. So what we could do, we could actually relax syntaxes by merging some of the nodes together and make parse like binary tree. Maybe we could even make larger spans which could intersect. Then another way would be to use, well, some precise tagging we had there. We didn't use it, we only used the parse. And another problem was that training data was rather sparse, especially when you use it as for language model. So it could be handy to add some backups to different places and to backup to other parts of speeches, use part of speech language model. So as an overview, we implemented this a tree-to-string reordering model based on Moses toolkit and gained substantial increase in all measurements over the baseline. We implemented some new features in Moses as well. So thank you for your attention. Any questions?